Hello everyone, I am DK Bhargavachari, a postgraduate from IIT Hyderabad. In this talk, I am going to present our work inferring DNN layer types through a hardware performance counters based side channel attack. This is a joint work with R. Sai Chandrateja, Sparsh Mittal, Biswabandhan Panda, and C. Krishna Mohan. First, let's have an overview of the talk. In this talk, we would briefly review how DNNs work, what are the core components of a DNN, the machine learning as a service model, while also touching upon the security concerns regarding the same. Then, we would try to understand how hardware performance monitoring counters can be considered a side channel. The talk would try to put light on the significance of data pre-processing and curating a dataset, then correlate the data of hardware performance monitoring counters to DNN architecture. To understand the proposed side channel attack, how can it be mounted in two phases? Finally, we would have a look at some interesting results from this work and summarize it. DNNs are some of the most widely used machine learning models for various applications, including some critical ones like healthcare, surveillance, defense, autonomous vehicles, and more. Here is a DNN architecture with several layers which transform the input into some output through a forward pass. One of the most important things to note here is that the features are learned by the DNN itself. For this, we typically need huge amount of data, and we also need to specify the architecture of the DNN suitably to learn the various features from the dataset. This approach is referred to as designing and tuning a DNN, which is highly resource intensive task and requires a lot of careful tuning. Since the architecture and hyperparameters determine the performance of a DNN, they are precious IP of the owner. The DNN's performance is also driven by data, which makes the data also precious. On the other hand, with the availability of fast internet and cost effectiveness of cloud infrastructure, machine learning as a service has grown in popularity, where a trained model is deployed in the cloud and is used for inferences by multiple clients without the fuzziness of managing or configuring many hardware and software systems. However, the cloud setup brings in some privacy concerns as there can be information leaks about the deployed DNN model through side channel attacks. Our work focuses on the reverse engineering of DNN architecture while they are deployed on the cloud as a service with a query interface. As we already mentioned, there are multiple layers that constitute a DNN, and each layer type in a DNN performs some different computations. A convolutional layer is basically a matrix multiplication layer where a smaller matrix known as filter slides over a larger matrix while performing multiplications. A pooling layer, on the other hand, is more like a downsampling layer where submatrices of specific size are combined into single values. The bottom line here is that each layer has a specific type of computational need in terms of computer hardware. Also, the DNNs are designed typically with some specific building blocks and design patterns. Like a convolutional layer is followed up with an activation layer and then maybe a pooling layer and so on. Can this information that we have on design patterns be exploited as a side channel attack? Let's see. Hardware performance monitoring counters are hardware registers present in modern machines to aid into the performance and workload analysis. The counters can be accessed through certain privileged instructions to count hardware events like cache misses, branch instructions executed, and so on. We also optimize the system configuration to make the attack work somewhat favorably without affecting the practicality of the work, like disabling the prefetchers. The core reasons of this study has been to understand if PMCs can act as a side channel and can they be used to understand DNN workloads. Moreover, can the PMCs help us reverse engineer the DNN architectures? We also intend to propose mitigations or design changes both at hardware and software levels. Let's establish the threat model at work here. We have a machine learning as a service-based query interface for an unknown DNN model running on a CPU. We assume the intruder to be the cloud admin who has access to the process ID and hardware PMCs. Even though the intruder has access to the hardware PMCs, there are certain challenges to make use of it. The DNN runs reasonably fast and the layer level operations happen even faster at a sub millisecond interval. The other issue is if we intend to capture these hardware events and make a dataset out of it, each layer executes differently. Some take more time, some take less time. The data would be highly imbalanced. Even if we overcome these problems, the raw data would have a lot of noise, as there might be other processes on the system. The number of hardware registers available for counting the various events is limited by number. Typically, there are 4 accessible registers in most CPUs for selectively counting more than 30 hardware events. That's another limitation. Now let's get into some of the details of this work. When we started with the base hypothesis of correlating hardware events to layers, the biggest challenge was the fast execution of DNNs. Initially, we worked with perf tools, which was limited to 1 millisecond interval for capturing the PMCs for a specific process. The details captured here were a starting point, but not significant enough to scale up and conclude. We tried CPU scaling by reducing the clock to the minimum and slow down the overall execution. We also tried disabling the prefetchers to avoid some noise from creeping in. We then added sleep layers in between each layer of execution in a DNN. Like after layer 1, there would be a sleep layer which would do nothing. Hence, no instructions would get dispatched, no cache misses would happen, no branch instructions would get executed. Then layer 2 would execute, and then again a sleep layer would come. And it continues like that. The addition of sleep layers was a key. With this, we could efficiently separate each layer of execution. And this was also scalable for any number of target DNN models. We added the sleep layers only during the preparation of the dataset, not in the inference phase. I would be discussing these phases in the next couple of minutes. But before that, let's see how part of a DNN trace looks like. We can relatively estimate from this graph or trace which layer has more cache misses, which layer has more branch instructions, which layer has less of it, and so on. The table given here summarizes some part of it. So we discussed that we had a problem with perf tools. The limitation was that we could only get through to 1 millisecond. So we discovered that using PAPI could enable 1 microsecond interval. PAPI is nothing but the performance API for capturing the PMC counts, which gave us a sufficient resolution. We also tried to apply filters in the raw data to iron out the intermittent fluctuations, which also helped to get better predictions. We dealt with the data imbalance problem by using Smote-based technique, which synthetically resamples the underrepresented classes. We initially tried curating the dataset in a supervised manner. However, that was cumbersome and not scalable. So we proceeded to automate it by splitting based on the intermediate sleep layers that we introduced and the reference DNN architecture information we already had. Like if it is a VGG16 that we're working with, we know that it has 5 convolutional blocks, each containing 2 or 3 convolutional layers followed up with a pooling layer. And then there is also activations in between. So we basically correlated the information to automatically figure out the labeling. We have made the dataset available in public domain for further exploration by researchers and academics. Now let's understand the attack, which has 2 phases, namely training phase and inference phase. This figure gives an overview of the training phase. The training phase includes multiple queries to a set of known DNN models and collecting the corresponding hardware performance counter traces, with a similar set of privileges as that of a cloud administrator. The collected traces are correlated with original DNN architectures to arrive at a reasonably large dataset, then perform the training of classifier like using a decision tree. Once we have attained a trained classifier, we are ready to move to the inference phase of the attack. In the inference phase, we make a query to the black box DNN with any valid input and collect the corresponding trace. We feed the trace to the classifier, which then recognizes it and gives information about the underlying DNN architecture. The attack is framework agnostic to a great extent, as we have tested the various deep learning frameworks like PyTorch and TensorFlow. This table summarizes the evaluation of a classifier on known DNNs. We train the ML classifier in the training phase with a set of traces from these DNNs like DenseNet, MobileNet v2, VGG19. Since the classifier is trained on these DNN traces, it was expected that there would be good predictions, which we see here. The numbers are representing the percentage execution time spent in the constituent layers of the DNN. We compare scores of the ground truth DNN to the reconstructed DNN. Although the accuracy of prediction is high, the classifier mispredicts on some instances. VGG16, for example, does not have batch normalization layer but is predicted with a low score. On the other hand, significant layers like convolution are predicted with a high score. Infrequently occurring layers are counted in the miscellaneous category. We do not distinguish between types of pooling layers or types of activation functions to simplify our observations. This table contains the evaluation of a classifier on those DNNs which the classifier was never trained on. Here we clearly see that the attack works well even on unknown DNN architectures, which is nothing but a reinforcement of our hypothesis. This figure shows the full PMC trace of a VGG16 network with a resolution of 0.1 millisecond covering all the constituent layers. Here we can visualize convolution layers shown in green, pooling layers shown in blue, and fully connected layers in pink shades. Now, moving on to the summary, in this work we demonstrated a side channel attack based on hardware PMCs. We employ the PMCs to derive traces of the basic network structure of the DNN model. Then the traces are used to train an ML classifier. Finally, we deploy the classifier to leak the layer pattern of DNNs in a black box setup. While doing all this, we curated a dataset of PMC traces for DNNs. Our classifier provides an accuracy of more than 90%. The knowledge inferred by our side channel attack can also help design an adversarial attack. Our future work will focus on proposing countermeasures of this attack. Thank you.